I don't think he did his homework, Tom.
Well, welcome. My name is Curtis Brown, and tonight we're talking a little bit about related rates. I've got Steve Kokoska with me and Tom Dick. Really excited to have these two guys here with me again, providing their expertise. I know Tom's going to jump in here in just a second with some technology, but if you are on live and you would just be so kind as to just interact in the chat, give me a little bit of information about where you're watching from, the maybe if you're a student or a teacher, be good information for us. If you are a student and you've got questions related to the questions that we posted, or maybe some other related, see what I did there, questions, related rates type questions, pop those in the chat. I'll make sure to get those to Steve and Tom. And finally, at the very end of this session, we will definitely be posting, or I'll post my email address. So for teachers, if you guys are looking for the professional development hours, just email me and I will send you that link. But I'll put that in there at the very end of the session. So Tom, I think it's up to you. You're doing the technology first tonight, huh?
Well, we're going to try it out. We're going to give it a shot here. So
All
let me
right.
go ahead
Oh, you know
and
what? I got to give you the ability to
okay.
share. There you go. Now you should have it.
All right.
What are we using first, Tom? The 84?
Yes, I'm going to go
Okay.
ahead and use the 84 here, and
Okay.
hopefully you all can see it all right there.
Yep.
Okay. Steve will go into the analysis of this in a little bit more detail, but let me go ahead and talk about his first problem. And it had to do with a train traveling along a track at and its speed is being given. Well, the track itself is in the shape of a graph, and we're given how fast it's moving with respect to the horizontal x coordinate. So
Correct.
let's take a look at the graph just to get a setting here. So the function that is in this problem, I've gone ahead and put it here in y1. It's 48 over pi, that number times the inverse tangent of the quantity x over 5. And so that's the graph we're going to take a look at. And I've gone ahead and set up the window so we have a decent picture of this graph. And let me go ahead back to the y equals and make sure I've got that actually activated. There we go. And there we go. So this is a nice picture of the graph of the track. And the train, I think it starts at the origin. It's moving along this track.
Mm-hmm.
And the question is, let's see, I think we're given that the x coordinate of the train as it's moving along the track, it's changing at the rate of 40 miles per hour.
Correct.
And we want to know how fast is its distance from the train station, which is at the origin. How fast is that distance changing? So I'm going to add an element to this graph just to get a sense of it. And the point we're interested in is when the train is at the point 5, 12, how fast is it moving away from the train station? So we know how fast it's moving horizontally, but we don't know how fast it's moving in the straight line distance. So I'm going to actually quit off the graph here and pull up the draw menu. And I want to draw in a line here, number 2. I want to draw a line from the origin, that's where our train station is, directly out to where the train is at when it's at 5, 12. And to draw a line on top of a graph like that, you just put in the coordinates of the beginning point and the end point. And you just enter those as 4 numbers. So the origin is 0, 0. And we're going to move to 5, 12. So you can see we're just listing the beginning and ending coordinates like that. We'll enter that. And notice what it's done. We still have our graph there, but now it's also drawn in the straight line distance from the station to that point. And we're really wondering how fast is that distance changing when the train's at 5, 12. Okay, so let's go ahead and try to calculate that using 84 here. So we have a function given here, but it's actually the function for the y-coordinate of the graph. And we're going to need actually the length of this diagonal-like line. I can think of that as the hypotenuse of a right triangle. The horizontal side would run out to 5, from 0, 0 to 0, 5, 0. And then from 5, 0 up to 5, 12. So I've got a triangle, looks like a 5, 12, 13 triangle. But remember, this triangle is changing as the train's moving. So I want to actually calculate as a function this distance from the station to the train. So let me move from the graph. Let's think about that. Pythagorean theorem. I think that's going to look like, well, let's see. First of all, we're going to want to take a derivative. We want to find out how fast this is changing. So let me go ahead and get the derivative pulled up here. And let's see, our function, our graph is in terms of x. And we know how fast, we know that the hypotenuse is going to be the square root of x squared plus y squared. So let me take the derivative with respect to x of that hypotenuse distance. Okay, so that's going to be the square root of x squared and while we're still under the square root sign, let's see, now I need the y value. The y value is also going to be in terms of x, but it's given by the value of y1 of x. So let me just pull up y1. Y1 is a function of x. Oops, let's see. Exponent there. And I want to look at this. Let's see, we're at the point 5, 12. So I guess we're at x equal 5. And let's enter that and see what we get. And we might be ready to cheer ourselves on and say, okay, we got it. We took this derivative, but we want to think about this. This is how fast the train is moving with respect to x. And remember, we want a speed, and x is changing with respect to time. So we want to take this derivative with respect to x times how fast x is changing with respect to time. That's the chain rule. So let's take this answer and multiply it by how fast x is changing, which is 40 miles per hour. And there we go. So that's giving us how fast the train is moving, actually that straight line distance from the origin straight out to 512, how fast that's changing at that instant. Now, I think I'm going to turn it over to Steve here in just a second here, but he's going to actually do a kind of a purely analytic solution. But we may want to come back and check and see if the numerical value of Steve's answer and this one, how close they look. But in case something forest got lost for the trees, this square root of x squared plus y1 squared, that is an expression, we can think of it as an expression in terms of x of the distance the train is from the station. We take the derivative of it with respect to x when x is 5, and then multiply by how fast x is changing with respect to time to get our final derivative. So this is how fast that distance is changing. Okay, so let me stop my share there and turn it over to Steve.
All right, thanks, Tom. I do have an analytic answer eventually for this. We'll have to check that to see if it works. All right, there we go. Can you see that one? Is that okay? Okay, very good. All right, so we're going to be working on some related rate problems, some optimization problems today. We've got quite a few of them. We've even got some overtime problems. I'm unsure whether or not Curtis finished his homework today, but I did post on Facebook for people to send him some help. So I don't know if anyone did or not.
Nobody emailed me any help today. That's
I'm sorry, Curtis. I tried to solicit some help for you.
I appreciate that.
When I do these problems in class, Curtis, my students find these difficult, I think, because most of these problems that involve related rates, that involve optimization, are word problems. And what students have to do, what I have to do, is to translate these words into mathematics, and it's not an easy task. So if you'd bear with me for just a second, Curtis, these are some of the things that I think about in trying to solve these problems. And as silly as it may sound, one of the very first things I think I have to do is to read the problem very carefully. What is it really telling me? What is it asking for? For me, I always try to sketch a figure. You can see mine on the screen, very similar to what Tom had. I'm going to add in a few extra things here by hand. The next thing I think I do mathematically is I try to introduce notation. I'm going to try to assign symbols to all the quantities that are given, all the quantities that are asked for, and think of them as functions of time generally in these related rates problems. I'm going to try to express the given information and the required rate in terms of derivatives, if that's possible. So generally in these problems, we're asked for a rate, a related rate to the problem. Well, then what I'm going to do is try to write an equation that relates all of these quantities that are in the problem. And if possible, what I want to try to do is to use the geometry in the context of the problem. And I try to eliminate one of the variables, if possible, by substitution. Not always, but if possible, I try to do that. And then perhaps the most important calculus step in all of this, I need to use the chain rule to differentiate both sides of my equation with respect to the variable t, with respect to time. And then finally, I put everything together. I use all the information that's given to me, and I solve the resulting equation for the unknown rate. So here we go. I'm going to try to actually do this. I won't enumerate, I won't put all of these steps into words here in each problem. But I am going to try to do this, use these steps. So I've drawn a picture for this one, and Curtis, as many of us do, we try to draw on our experience here for these problems. And this train, this MBTA train, this trolley, did indeed leave Chestnut Hill just at the bottom of the Boston College campus. And in fact, it did kind of follow a track like this as I think about it. It did kind of look like that. And I don't know how fast it went, but I looked this up. And they do generally travel between 40, 50 miles per hour when they get going.
Right.
So, all right, I drew a picture as Tom did. If you can see that on the screen, that blue curve is the track. That's the track that the train is following. The station is at the origin, 0, 0. I'm given that the rate of change in the x direction is 40 miles per hour. So there's dx dt. There I'm expressing the given information in terms of a rate. I'm going to let z be the distance to the train station. So there's my line that Tom drew in. That's z. And yeah, Curtis, I admit I'm still old school. I still put a little mark in the middle of my z's.
Hey, so do I, and so do I, Steve. My handwriting, it's hard to tell a 2 from a Z.
Exactly, exactly. And let's see, I want to find, when this is all done, I want to find dz dt. How is that distance from the station changing at this one particular instant when the train is at the coordinate 512? Okay, so I've got to come up with some sort of equation that relates a lot of these variables, relates using geometry and in the context of the problem. So my equation is this one: z squared is equal to x squared plus y squared, as Tom mentioned, using the Pythagorean theorem. Now I'm kind of lucky here because I have an expression for this distance y, that point on the curve. That's this expression right here. That's the y value for any given value of x. Well, that's good. I've been able to eliminate one of the variables. Give me just a second here, Curtis. I'm going to try to arrow up just a little. So now what I'm going to do is I'm going to take the derivative of both sides of this equation, thinking of all of my variables here as functions of time. So all right, on the left-hand side, use the chain rule, 2z to the first power times the derivative of the inner function with respect to t. So that's dz dt. On the right-hand side, 2x times the derivative of x with respect to t, dx dt. And now I'm going to take the derivative of this expression. Boy, lots of chain rule action going on here. Bring the 2 down, times the inner function to the first power. I'm going to put in a little 1 there. Times the derivative of the inner function. Don't let me make a mistake on this one. There's the constant, 48 over pi. Let's see, the derivative of the inverse tangent of an argument is 1 divided by 1 plus the argument squared, there it is, times the derivative of the argument, 1/5, times inner function, derivative of x with respect to time t. Holy Toledo. Now, I'm going to do a little simplification here. That's probably the hardest part. I can certainly get rid of the 2's. And notice that I still have a z here. So I've got to find that value of z at this instant when the train is at 512. And of course, I picked this kind of nicely. So at that instant, when x is 5 and y is 12, z is going to turn out to be 13. And now I'm going to plug everything in. I've got a value for z. I've got a value for x. Yeah, that's in my equation up here. And I know dx dt at this instant, that's 40. So I'm going to plug everything in here and see if this works, okay? All right, let's see here. There's the 13 for z. That's what I want to solve for. Let's see, x is 5, dx dt is 40. 48 over pi, yep, tangent inverse x was 5, so that's the tangent inverse of 1. 48 over pi, 1/5, let's see, 1/2, is that right? Yes, when x is 5, that's 5 squared over 25, so yep, 1 plus 1, that's a 1/2, and there's a dx dt on the end there, that's a 40. Holy Toledo. So I did a little bit of simplification here on the right-hand side. I'm going to divide everything by 13, and I think there's my symbolic answer for dz dt. How about that? So that is the rate at which the distance between the train and the station is changing at that instant when it's at that location 512, which is pretty cool. Tom, do you want to check that on the calculator before I try number 2?
Sure, let's go ahead and take a quick look.
I just checked your work, and the decimal value does come out. So
it does. Okay. Very good.
That's good. Good work there.
Okay. All right. Well, in that case, let's take a look at number 2. Tom, chime in anytime when you want to do another technology piece here.
Okay.
So we know that our friends up north, Curtis, are suffering from some of this cold and snow, so we felt it would be appropriate to do a snow problem.
We do have a group on from Maine tonight, so
well, that's chilly up there.
A bunch of calculus students from Maine are on tonight.
Very good. Very good. What part of Maine? They're not Brendan Murphy students, are they, by any chance?
I don't know. They may pop in the chat here and let us know. We've also got Jordan from Taiwan, so
we've
also got folks from below the equator on. So
wow, terrific.
Yeah.
Terrific. All right, well, it's a cold and snowy day in a big city, and a person is standing at the base of this 240-foot office building. And all of a sudden, a chunk of snow falls from the top of the building straight down. And the person just happens to be looking up at that time. And as soon as that chunk starts to fall, they start running immediately away from the building in that direction. All right. So they're running at a velocity of 8 feet per second, which is pretty reasonable. If the height in feet of the snow chunk at time t is given by this expression, at what rate is the distance between the person and the snow chunk changing at time t equal 3 seconds? So this one's just a little bit different than the previous one, although we are going to use the Pythagorean theorem again. Here we are out here at this point when t is equal to 3. I'm going to draw in this line here. I'm going to call that z. That's the distance between the person and the snow chunk. And once again, that's the rate. We want to know, how is that rate changing? I've got my picture here. I said I'd try to draw one so you can see the office building. S of t represents the height of the snow chunk at time t. And we know that dx dt is equal to 8 feet per second. That's the rate at which this person is running in that direction. So I need to find dz dt when t is equal to 3 seconds. All right, let me arrow up here a little bit, see if I can get this to work. Hey, how about that? Here we go. All right. So we know that the height of the snow chunk, okay, one more thing that was given to me in this problem is given by this expression. Curtis, any idea where that expression might have come from? I don't think I made that up just out of thin air.
I wasn't looking, but just looking at the negative 16 t squared, that seems an awful lot like acceleration due to gravity. So
beautiful. Absolutely. Yep. So it is a little bit realistic here. Very good. All right. So here we go. What's my expression for z squared? It's x squared plus, in some sense, y squared, but that's the height of the snow chunk. So this is an interesting problem to me because this has a z in it, it has an x in it, and it has an expression already in time t. So remember, what I'm going to do here is to take the derivative of both sides with respect to t. And so this one already has an expression in t a little different than many of the related rate problems that we see on the exam. So here we go. On the left-hand side, 2 times z, derivative of z with respect to t. On the right-hand side, 2x to the first power times the derivative of the inner function, dx dt. Derivative with respect to t, chain rule, 2 times the inner function raised to the first power times the derivative of the inner function. Let's see, minus 16 times 2t minus 32t. Beautiful. How about that? All right. I've got to plug in for all of these variables some values that I have known. We know that t is equal to 3. When t is equal to 3, we know that x is equal to 24, right? Because this person was running at a rate of 8 feet per second. So their distance would be 24 feet. And the height of the snow chunk, I'm going to use that expression for s of t. It's going to be 96. Well, this one doesn't work out quite as nicely as problem number 1. I've got to find a value for z. Let's see, using x and y squared, the height of the snow chunk, I think it works out that z is 24 square roots of 17. All right, I'm going to put it all together. Here we go. I apologize for this, Curtis. I'm going to sneak back up here just a second. I can get rid of all those 2's. I can divide out by a 2, so that's why you don't see an extra 2 in this equation. So let's see. There's my value for z. Here's my unknown quantity. There's a value for x. There's dx dt. And let's see. Here's the value for that expression inside the brackets. And minus 32 times 3. Solve all of that for dz dt. There is my analytical expression. It's minus 91.193 feet per second. Let's just think about that for a second. Can we interpret that in the context of the problem? What does that mean about the snow chunk in relationship to the distance to the individual? Since it's negative, what does that mean? It's actually doing what? Curtis, any chance you can interpret that in the context of the problem?
I would assume it's getting closer
Very good. Yeah, which is kind of weird, but it is indeed getting closer to the individual. Still not going to hit them, but
it's not too weird, right?
okay. Yeah, the snow chunk
at that moment in time, right? We're asking that question at that moment in time.
Right. Right. Okay. Very good. I like that. All right. Two good, I think,
I have
related.
more questions about that.
Steve. Oops,
Yes.
sorry.
I have more questions about that.
Oh, uh-oh. Okay, go ahead.
Is there a point at which the snow chunk starts getting farther away before it hits the ground?
Well, that's a good question.
I mean, obviously, once it hits the ground, the guy's still running away, then fine. But that's
So,
just
Steve, would it be okay to pull the technology in here for a little bit?
Let's see if we can do that. Absolutely.
Okay. All right. So, Steve, I noticed that you mentioned that actually, if you could pull the problem back up there, Steve.
Oh, sure. Sorry.
You do something. No, that's all right. I should have said something.
Okay, go ahead.
So you mentioned that the height of that chunk of snow is already given explicitly as a function of t. That's your S of t.
Correct.
Is there any way we could get x as a function of t? That would be the horizontal distance from the building. Well, your very first line there says dx dt is 8 feet per second. So the derivative is a constant 8. That means my x is going to have to be 8t plus some constant. Well, we know when t equals 0, x is 0. So actually, x of t equals 8t is an explicit function for x in terms of t.
Mm-hmm.
If we put those together, that means we actually could write z in terms of t. So I thought maybe we could take a look at that on the calculator, and then it would also be a way of checking your answer numerically, see if it works out.
And we might even be able to answer. Could we answer?
And then we could answer Kurtz's question too, I think.
Okay, very good.
Right. Good.
Okay, so I'll
there you go.
I'll share my screen and go back to the 84. By the way, there's that numeric check of number 1.
How about that?
And it came out pretty darn close. There was only a little bit of a difference in
the last 2 decimal places there.
And pretty amazing. All right.
Pretty good. Pretty good.
So what I'm going to do is go ahead and pull up a derivative again. And we're going to take the derivative now with respect to t. And what I'm going to put here in is my function is what is that distance z in terms of t.
Okay.
So it's going to be a square root. Mm-hmm. And let's see, the x, I think, was just 8 times t.
Right.
And we'll need to square that.
Yep.
Yep.
Then we'll take the s, which was negative 16 times t squared.
Right.
Plus 240.
Mm-hmm.
240. Mm-hmm.
And then we'll take that quantity squared. Mm-hmm. And that's actually, that whole expression is giving us that distance between the snow chunk and that running person totally in terms of time t. Now, it's not often you can do that in a related rates problem, but this one kind of lent itself to us being able to get that. And let's see, I think we were interested in what was happening at t equals 3.
Right.
And let's go ahead and see what we get. Oh, that number looks familiar.
Holy Toledo. How do you like that?
Yeah. Very cool. Very cool.
That's
and
really
then alternatively, we could graph this function And I think to save some time here, let me just go ahead and use y1 again. I'll do it as a function of x, but it's actually going to be a function of time, right? So I think we had 8. So remember, x is playing the role of time t now. So 8x squared under the square root sign plus negative 16 x squared plus 240. Let's just take a look at that. I think that looks all right.
Okay.
And let's see, just for the heck out, I'll go ahead and let's see. Well, our window, what should we do here? I'll tell you what, I'll just go ahead and do a zoom decimal window here real quick, but then we'll need to adjust, I'm sure. Oh yeah, it's going to be way off. The distance between the snow chunk and the person's going to start out being 240, right?
Right.
Okay,
Right.
So we really do need to change this window. So let me make my x min 0. That's when time starts.
Mm-hmm.
And I'll go to, let's say 10.
Mm-hmm. That's good.
And then for the y range, let me go from 0 to 240. And I'll make my y scale something reasonable like 20. There we go. Let's graph that. Oh, all right. Okay. Very interesting. Okay, now what is this graph of? Well, it's the distance between the snow chunk and the person as a function of time. But I'm suspicious about this bounce up here. What do you think's going on there? Is this model look reasonable at all? Is there any problem with it? Any ideas, Curtis?
Well, I think that was the question I had was there a time when the distance between the person and the object and the snow chunk began to increase before the object hits 0. Eventually it's got to start increasing, right? Because once the object hits the ground, the guy's still running away.
Exactly. And this
so I'm gonna hypothesize that minimum there is maybe slightly before the object hits the ground.
Yeah, and can we figure out when would that, let's see, what would be the time that it would take for it to hit the ground? Let's see, the original, I'm just going to go back to y equals. It's this second part, negative 16, and remember x here is time. It was negative 16t squared plus 240. When does that part become 0? Well, I think if I solve that inside piece of the parentheses equal to 0, I'm going to get x squared equals 15. If I do my calculation in my head.
Yep.
So when time equals the square root of 15, that's when the snow chunk has hit the ground. Now, what number is that? Let's see. Actually, I wonder, can we actually do that? If I go back to the graph and do a trace, can I actually put in the square root of 15? Correct. Yep. Let's try that out. See exactly where that is. Oh, it's right. That's interesting. Okay. And from there on out, this model really doesn't make any sense anymore.
It does not, right?
Right. And that's really when thing stop. And in fact, now we know that it's actually, this would be a piecewise function. At that point, the snow chunk is resting on the ground, and that guy is still running at 8 feet a second away. So,
Right.
So I think that is the closest that it got to him, was
at the point that it hits the ground.
Right.
And this is that actual distance. It was about 31 feet away from him when it hit the ground.
So here's all right. We made an assumption about this guy, and I don't want to get too far into the middle of all of this, but we made an assumption about this guy that the point we're talking about him, is on the ground, right? Because it was 240 feet above the ground when it began to fall, right? And he doesn't actually, and I assume it's a guy. We just all of a sudden decided it was a guy.
Yeah, we shouldn't have.
The person was decided to start running away, but we didn't give him an initial a height, right? So he's not above the ground at all. And so perhaps I should have predicted that. I only just now kind of came up with that thought. If we'd have given him a certain amount of height above the ground, like his head was 6 feet above the ground or something.
Oh,
that could then,
that would have
because he at that point he is going to have there's going to be a point when it passes 6 feet, right, and then it's going away from him at that point.
Right.
Anyway,
that's a great thing for tomorrow morning at 8 a.m.
There you go.
To change the problem slightly.
Yeah, make him 6 feet tall.
Yeah, well, let's make it Yao Ming running away, so it's 7 feet tall. And let's see what happens. Okay. That's a great idea. That is a great idea. All right.
All right, back to you, Steve.
Okay, thanks. Here we go. All right, Curtis, we're going to take a look at a couple of optimization problems here now. I don't know how far we'll get with these. We do have some overtime problems too. We probably won't get to those, but let's try this one. The rate in milligrams of carbon per meters cubed per hour at which photosynthesis takes place for a certain species of tree, evergreen trees, given by this function, where I is the light intensity. One might think that the greater the light intensity, the greater the rate of photosynthesis. So I'm going to circle this word here because this is a little unusual. Circle this. P is actually a rate here, not a quantity, but it is a rate. So we want to know if we can find the light intensity that produces the maximum rate of photosynthesis. So in essence, what we want to do is to maximize this value of P. So what I might do first here in solving this problem is think a little bit about what is the domain for P here. And I guess I think about it as I is greater than or equal to 0. The light intensity could be 0. It's not going to be negative. Theoretically, there is no upper bound, but there must be practically in thousands of foot candles. But we'll just say it's greater than 0, greater than or equal to 0. So how do we do this? We're going to start off by taking the derivative of P with respect to I, and let's think about this. This is really a rational function. It's the quotient of two polynomials. We're going to take the derivative using the quotient rule, and I'm just going to abbreviate and scribble a little bit off to the side. I'm going to use the quotient rule here. So I'm going to bring the denominator up. I'm going to multiply by the derivative of the numerator, which is just 200. I'm going to subtract off the numerator, 200i, derivative of the denominator. Derivative of the denominator is the derivative of a polynomial, derivative term by term, so 2i plus 2. All of that divided by the denominator squared. In the interest of time here, Curtis, I'm going to do a little bit of simplifying up there in the numerator. And some good things happen here. I can actually factor out a minus 200. And in the numerator, I'm left with I squared minus 9, which I can factor. That's the difference of two squares. And now the way that I attack this one is I've got to find the critical points. Remember that a critical point or a critical value is a value where the derivative does not exist or equals 0. So this derivative is equal to 0 only where the numerator is equal to 0 and the denominator is non-zero. That occurs at 3 and minus 3, but I'm going to throw out the minus 3 because, darn it, that's not in the domain of this function. And there are no places where the derivative does not exist. That sounds kind of funny. So my only candidate here that I'm going to take a look at is, well, really I equal 3, and I'm going to think a little bit about a number line. And I did not draw this here, but that's certainly acceptable, and that certainly helps me with this analysis, this analytic approach. I would draw a number line something like this. Over here at 0, here's I equal to 3, and I know that the derivative is 0 there. And I'm going to try to look at, I generally look at this factored expression for the derivative to try to determine what's the sign of P prime in these intervals. Well, it turns out that P prime of I is greater than 0. It's positive in this interval, and it's negative over there in that interval. I get to ask this question frequently by my students, Curtis. Well, don't I have to check any other places here? Like, what about at I equal to 17? And the answer is no, you don't have to look anyplace else. Because the only place where this derivative can change sign is at a critical value, where the derivative is 0 or where it doesn't exist. So I don't have to look anywhere else. I can see that the derivative is positive and then negative. So I can see that there is indeed a maximum rate of photosynthesis at the time, or at the value I equal 3. Tom and I are often asked, well, what do you actually have to write on a free response question if you had something like this to get full credit for your justification? And I'd just like to remind, especially the students, that, it is certainly okay to draw a sign chart, and son of a gun, sign charts help me. But a sign chart is not sufficient justification. What you must do on the exam is you must interpret that sign chart by writing an expression something like this. Many of the students out there, you're better at this than I am, and you may be able to go directly to this sort of expression without writing any sort of a sign chart, and that's terrific. But you do need to write some sort of a justification, something in words here that justifies why I equal 3 produces that maximum value of P. Cool. Tom, any technology there? Should I try number 4? Oops.
Uh-oh.
Yeah, why don't you go ahead to number 4, Steve?
That's okay. Fine. All right. Let's take a look at 4. All right. I like this one a lot. My brother-in-law is a big fisherman, and we actually talked about this problem. So for a fish, swimming with velocity v relative to the water, we think about the energy that must be expended, and it's usually proportional to the velocity cube. That's actually been investigated, I think, empirically, and that's actually a true statement. So let's suppose a fish is swimming against a current that is 10 feet per second. So you think about these salmon that are spawning and swimming upriver. Then the time required to swim 200 feet is given by that expression, 200 divided by v minus 10. The total energy required to swim this distance is given by this expression right here. We'll call it E of v. So let's see if we can determine the value of v that minimizes the energy expended. So there is some question about, somehow does nature know this? Do they know what velocity here to swim at in order to minimize their energy expended? Well, let's see here. First of all, again, I'm thinking a little bit about the domain for E. What's the domain? Well, the velocity's got to be greater than 10, right? Because if it's 10 or less, they're not making any headway. They're not going to be able to swim upstream. So it's got to be greater than 10. So here's my expression for V. I did a little bit of, simplification or rewriting. So that now this is again a rational expression in V, the quotient of two polynomials in V. How do I take the derivative? Well, I've got to use the quotient rule once again. Bring the denominator up, derivative of the numerator, 600V squared. Yep, that looks right. Minus the numerator times the derivative of the denominator. Hey, that's pretty easy. The derivative of the denominator here is just 1. And a little bit of simplification. And here's what I have over here, what I might call my completely factored form. And it's not really that complete because I actually could take out a 2 out of that expression in the denominator, but it's good enough for me right now. So let's see, what are the critical values here? Where is that derivative equal to 0? Well, the derivative is equal to 0 where this expression is 0. That would be 30 divided by 2 or 15. And I'm going to add in a little bit over here, and then I'm going to cross it out. It's also 0 at V equals 0 because this is a product. How do you make a product 0 only if one of the terms is 0? But we know that 0 is not in the domain here, so we don't have to worry about that. Are there any places where the derivative does not exist? Well, you might say, well, what about 10? But I'm going to respond to that and say, well, 10 is not in the domain, so I don't need to worry about that at all. So I have one critical value. Now, I didn't draw a sign chart for this one. Here's a problem again for 8 o'clock tomorrow morning. But it turns out that the derivative is less than 0 for V in that interval. It's greater than 0 for V in that interval, so it turns out that the derivative is negative and then positive. And so, in fact, there is a minimum when V is equal to 15. And that's pretty cool. It seems to me kind of naively here that the fish would have to swim a lot faster than that. But it turns out that swimming at 15 feet per second minimizes the expenditure of energy, which is pretty cool. Well, you know, Curtis, you know me, sometimes I like to confirm some of this graphically. And so what I did is I tried to sketch a graph of E, and here it is. So we know that the domain is greater than or equal to 10. So on my horizontal axis, I have V. On the vertical axis, you'll notice those values for E are very large. There's a V cubed in there. So one would expect them to be very large. It's kind of hard to see, but in fact, there is a minimum value right there. Here's a nice question here in the context of the problem. It surely looks like at V equal to 10 that there is a vertical asymptote. And in the context of the problem, let's see if I can think about this just a little bit. As they get closer and closer to 10, as the velocity of the fish gets closer to the velocity of the stream, the expenditure of energy is greater. Does that make sense? Yeah, harder and harder to sort of maintain and travel that distance. I need a lot of energy to combat that stream movement. I think that's correct. Pretty cool. All right, and I have a part C here too, Curtis. One of the types of problems that we've been seeing, I think we've talked about this a couple of times. One of the types of problems we've been seeing often on the free response portion of the exam recently is where we get a lot of extra variables. And we're often asked to solve, students are often asked to solve or find an equation, solve something in terms of these variables. So let's suppose that for any distance L and any current U, then the energy required is given by this expression. So there's my variable L, a constant. There's my variable U, the current, the stream current U. Show that the value of V that minimizes E is approximately 3/2 U. It turns out, sorry, Curtis, I got to get this in there. It turns out that empirical data suggests that, in fact, this is true, that the velocity of the fish should be about 3/2 times the stream current to minimize the expenditure of energy. And evidently, through observation, this is proved to be pretty darn accurate. This is amazing. So the domain here is V greater than U. There's my expression for E. Again, I've got to take the derivative with using the quotient rule. Here it is completely factored. What are the critical values? Well, V is equal to 3/2 U. I'm going to add this in here again. V is also equal to 0, but I can get rid of that. And if you think a little bit about a sign chart, you'll see that the derivative is in fact negative to the left of 3/2 U, positive to the right. And so it is, the function E is in fact decreasing and then increasing. And there is indeed a minimum at 3/2 U. That's kind of a neat real world practical problem, I think, based on some real data. I like that one. Tom, a little technology?
Well, just maybe a technology note on here is it might be interesting to actually graph this, and I think you're going to graph it, but I would just have people pay attention to what kind of scaling you had to use on this graph.
Yeah, exactly.
That would be the point I would. So you might want to actually compute a few values to get a handle on what a Y range should look like. So.
Yeah, good point. I think when I first did this, it was off. I didn't see anything. It was way off the screen.
Yeah.
Okay, well, wait a minute. There's a V cubed in here. Yeah. All right, one more, Curtis. Let's see if we can do number 5 here. This one is actually, I think, also kind of realistic. So we all have our cup of coffee in the morning. I know, Curtis, you're a big coffee fan.
I do enjoy
some
coffee.
So if caffeine is ingested, for example, in a cup of coffee, it turns out that the blood concentration of caffeine C rises and falls over time, as one might expect. And it turns out that it can be modeled pretty closely by this equation. Yep, those are E's in there, so those are exponential functions. Alpha is referred to as sort of the absorption rate, beta is the elimination rate, and D is the size of the dose or the amount of caffeine, okay? So let's suppose that D is equal to 80 milligrams. That's generally the amount of caffeine in a typical cup of coffee. Usually, I think they say it's around 80 to 120 milligrams, but let's go with the 80. Let's suppose that alpha is equal to 0.95 and beta is equal to 0.3, and let's find the time t at which the concentration of caffeine is a maximum. So I might want to know this as I'm preparing to take an exam. I want to take my cup of coffee at just the right time. So when I get in there and start, man, my caffeine is at its highest concentration and I'm ready to go, right? So here we go. Some cool stuff going on here. I'm going to plug in all these values for alpha and beta, and I'm going to get an equation that kind of looks like this. And that's the equation that I want to maximize. So again, this is kind of a cool optimization problem. So let's see, what do? I have to take the derivative of that equation. So there's the constant out in front. How do I take the derivative of these exponentials? Well, the derivative of that is the exponential function times the derivative of the inner function, the derivative of what's up there in the exponent. And these aren't too bad. It would just be that constant. In this first case, minus 0.03. Minus 0.095. 0.95 e to the 0.95 minus 0.95 t. And let's see, how do I make that equal to 0? Well, at first glance, I might look at this and say, well, wait a minute, this has got exponential function in it. It's never going to be 0. But wait a minute. I'm going to take this expression on the inside and I'm going to set it equal to 0. Can I do anything here? Now, Curtis, forgive me on this one. I may have done this in a very long-winded way, but I wanted to do this so that even I could understand this. So here's what I did. I took these exponential functions and I noticed, well, wait a minute, there's a negative exponent, so I'm going to write them in the denominator. I noticed that there's still a minus sign out front there. These two minus signs, well, that becomes a positive. I'm going to bring one of these to the other side, and now I've got this expression. Now I'm going to cross multiply, holy Toledo. And now I'm going to take the log of both sides, the natural log of both sides. Why did I do that? Well, I guess my thinking is somehow I've got to bring that t, that unknown variable, t down to sort of what I call the base. That's my weird way of thinking about this. And I've used some properties of logarithms here. The log of a product is the sum of the logs. And I know that the log and e, the natural log, and the natural exponential functions are inverse functions. So there's my 0.3t.
Right.
The other side similar. And now what happens here? Now I bring my constants to one side. I factor out my t, do a little bit of division, and I get t is equal to 1.773. Now, one thing I didn't do here, and we'll leave this for the students, how do I know that that value of t produces a maximum value of c? I didn't put a sign chart down here. I didn't use any justification down here. You might think a little bit about what the domain is for this function c and write in some extra justification to make sure that that does indeed produce a maximum concentration. Cool.
I'm curious, Steve.
I gotta know, are those constants things that you looked up, or are those like the alpha and beta there?
No, they are actually pretty reasonable. I believe that the absorption rate tends to be much higher than the elimination rate.
And those are in terms of milligrams per minute? Milligrams
per yeah, I'm gonna say minute, but I forgot.
I'm curious. I was curious on, of course, the units eliminate, I think they kind of take care of themselves here. But
well, it would be good to know that this is 1.7 minutes or 1.7 hours, but I'm pretty sure it's minutes.
I'd be very, I wonder.
Yeah. Yeah. Okay. Good question. All right. Well, here's a graph just to justify all of this. That's what it looks like. And we'll assume the t is given in minutes here. And let's see. In C, what I did, and we will post these, of course, tomorrow, Curtis. In C, what I did is I did this in a much more general way, like we did the previous problem. We left alpha and beta and d as general unknown constants. And it turns out that the value of t that maximizes the concentration is right there. The log of alpha divided by beta over alpha minus beta. Very cool. All right, some good problems for tonight. I'll just mention quickly these two overtime problems, and we'll put these solutions up tomorrow morning, Curtis, I guess.
Yep.
This was on the Facebook page, and I've seen a number of problems like this recently. Here we have a graph of f prime, and we know that f of 0 is 9. Can we find f of 2? We see a lot of problems like this on the free response portion of the exam, often associated with particle motion problems on a horizontal line. I think of these, Tom and I have talked about this frequently, I think of these actually as a fundamental theorem of calculus problem. I write as the integral from 0 to 2 of f prime of x is f of 2 minus f of 0. I know f of 0, and I can find this using the geometry in the problem, and I solve for the unknown f of 2. So that's a very typical sort of a problem. This was on the Facebook group, and I thought I would put an answer to that one out there. And this was also kind of a neat problem. Here we have a function that is defined piecewise in terms of two unknown constants a and b, and we want to find a and b so that f is both continuous and differentiable at x equal minus 1. And then to make this a real AP calculus type question, what's the sum a plus b? I don't want to know just what a and b is. I want to know the sum of a plus b. So we'll post these answers tomorrow, but I wanted to point out one other thing here, Curtis, before we leave this. One of the concepts, one of the ideas in the course and exam description is notational fluency. And we actually had a problem. I think Tom and I worked on this one together last year, where we were wondering about the left hand and the right hand derivative of a function. And we were wondering what type of notation to use. And I think that this kind of a notation right here is what you might see for the left hand and the right hand derivative of a function at x or at a value. So it's kind of f prime with a little negative symbol from the left, f prime with a little plus sign for taking the derivative from the right. All right, great, Curtis. Thanks for your patience. Great technology tonight, Tom. Excellent. Any other last minute questions, Curtis?
I have not seen any more questions come through the chat, Steve. So
Okay, very good.
I went ahead and put the link to the next session, which will be February 12th, 7 p.m. I believe we'll be chatting that evening about accumulation problems. We'll be looking at these growing things we have happening in that session. So looking forward to that session here in a couple of weeks. I will be posting the solutions as soon as Steve sends them to me in the morning. So we'll make sure that those are in the description down below. Also, teachers for the professional development certificate, you can certainly email me at my email address. I'll drop it here in the chat. And let's see, I don't know that there's anything else that I need to say, except for make sure that you invite your friends and your students. We'd love to have more folks on live on these sessions. I know a lot of folks watch them though, sort of on demand later on. So happy to have the folks watching them any way that's good for them. So thank you guys again for this evening. And, we'll see you guys in 2 weeks.
Beautiful.
All right.